The Sun and Space Weather, Part 2 of 2. The Sun and its atmosphere consist of several zones, or layers, from the inner core to the outer corona. Beyond the corona is the solar wind, which is an outward expansion of coronal plasma that extends well beyond the orbit of Pluto. This entire region of space influenced by the Sun is called the heliosphere. Controlled by the Earth's magnetic field, the magnetosphere acts as a shield protecting the planet from solar wind. The shape of the Earth's magnetosphere is the direct result of being impacted by solar wind, compressed on its sunward side and elongated on the night side, the magnetotail. The shock wave where the solar wind encounters Earth's magnetosphere is called the bow shock, which slows and diverts the solar wind. Solar activity leads to solar eruptions, which include such phenomena as sunspots, flares, prominences, and coronal mass ejections that influence space weather, or near-Earth environmental conditions. Modern society depends heavily on a variety of technologies that are susceptible to space weather. CMEs, for example, can cause geomagnetic storms that can disrupt satellite communications and navigational equipment, and even cause blackouts. 3 types of space weather storms. 1. Radio blackouts. 2. Solar radiation storms. 3. Geomagnetic storms. Radio blackouts. Sun releases electromagnetic emission like X-rays through solar flares, impacts, aviation, atmospheric drag, radio frequencies communication outage. Solar radiation storms. Sun releases charged particle radiation through solar flares or coronal mass ejections, impacts, human space exploration, data corruption, satellite electronics damage, airline passenger radiation, solar panel degradation. Geomagnetic storms. Sun releases magnetized plasmas or clouds through coronal mass ejections, impacts, global positioning system, GPS, signal, power grids, atmospheric drag, satellite electronics damage. Radio blackouts. Radio blackouts are caused by bursts of X-ray and extreme ultraviolet radiation emitted from solar flares. Radio blackouts primarily affect high-frequency, HF, 3 to 30 MHz, communication, although fading and diminished reception may spill over to very high frequency, VHF, 30 to 300 MHz, and higher frequencies. These storms are a consequence of enhanced electron densities caused by solar flare emissions. The emissions ionize the sunlit side of Earth, which increases the amount of energy lost as radio waves pass through this region. Radio blackouts are among the most common space weather events to affect Earth. Minor events occur, on average, 2,000 times each solar cycle. Blackouts are by far the fastest to impact our planet. The X-rays creating radio blackouts arrive at the speed of light 8 minutes from Sun to Earth, making advance warnings difficult. When flares occur, however, SWPC measures their intensity and forecasts their duration. Usually the radio blackouts last for several minutes, but they can last for hours. The impacts of radio blackouts are felt by industries relying on HF radio communication and low-frequency signals, primarily the aviation and marine industries. Solar radiation storms. Solar radiation storms occur when large quantities of charged particles, protons and electrons, are accelerated by processes at or near the Sun like solar flares and coronal mass ejections. When these processes occur, the near-Earth satellite environment is bathed with high-energy particles. Earth's magnetic field and atmosphere offer some protection from this radiation, but the amount of protection is a function of altitude, latitude, and magnetic field strength. The polar regions are most affected by energetic particles because the magnetic field lines at the poles extend vertically downwards, allowing the particles to spiral down the field lines and penetrate into the atmosphere, increasing ionization. Energetic protons reach Earth a half hour to several hours after a solar eruption. Solar radiation storms can last from a few hours to days, depending on the magnitude of the eruption. Solar radiation storms can occur at any time during the solar cycle but tend to be most common around solar maximum. Solar radiation storm impacts include loss of HF radio communications through the polar regions, navigation position errors, elevated radiation exposure to astronauts and to passengers and crew in aircraft at high altitudes and latitudes, and damage to satellite systems. Geomagnetic storms. A geomagnetic storm is a major disturbance of Earth's magnetosphere that occurs when there is a very efficient exchange of energy from the solar wind into the space environment surrounding Earth. These storms result from variations in the solar wind that produces major changes in the currents, plasmas, and fields in Earth's magnetosphere. The solar wind conditions that are effective for creating geomagnetic storms are sustained, for several to many hours, periods of high-speed solar wind, and most importantly, a southward-directed solar wind magnetic field, opposite the direction of Earth's field, at the day side of the magnetosphere. This condition is effective for transferring energy from the solar wind into Earth's magnetosphere. A geomagnetic storm is a temporary disturbance of Earth's magnetic field typically associated with enhancements in the solar wind. These storms are created when the solar wind and its magnetic field interacts with Earth's magnetic field. The primary source of geomagnetic storms is CMEs, which stretch the magnetosphere on the night side, causing it to release energy through magnetic reconnection. Disturbances in the ionosphere, a region of Earth's upper atmosphere, are usually associated with geomagnetic storms. The Northern and Southern Lights. An aurora is a natural display of light in the sky that can be seen with the unaided eye at night. An auroral display in the northern hemisphere is called the aurora borealis, or the northern lights. A similar phenomenon in the southern hemisphere is called the aurora australis. Auroras are the most visible effect of the sun's activity on the Earth's atmosphere. Most auroras occur in far northern and southern regions. The most common color in an aurora is green. But displays that occur extremely high in the sky may be red or purple. Most auroras occur about 50 to 200 miles above the Earth. Some extend lengthwise across the sky for thousands of miles. Auroral displays are associated with the solar wind, the continuous flow of electrically charged particles from the sun. When these particles reach the Earth's magnetic field, some get trapped. Many of these particles travel toward the Earth's magnetic poles. When the charged particles strike atoms and molecules in the atmosphere, energy is released. Some of this energy appears in the form of auroras. Auroras occur most frequently during solar maximum, the most intense phase of the 11-year solar or sunspot cycle. Electrons and protons released by solar storms add to the number of solar particles that interact with the Earth's atmosphere. This increased interaction produces extremely bright auroras. Space weather impacts on Earth. Space weather is a global issue. Unlike terrestrial weather events, like a hurricane, space weather has the potential to impact a wider geographic regions. These complex events can have significant economic consequences and have the potential to negatively affect numerous sectors. Electric power. Large currents in the ionosphere can induce currents in power lines. Surges from these induced currents can cause massive network failures and permanent damage to electric grid components. Navigation systems. Disturbances in the ionosphere can cause degradation in GPS range measurements and, in severe circumstances, loss of lock by the receiver on the GPS signal. Aviation. Space weather storms can cause lost or degraded communications, radiation hazards to crew and passengers, unreliable navigational information, and problems with flight-critical electronic systems. Human space exploration. Energetic particles present a health hazard to astronauts on space missions as well as threats to electronic systems. During space missions, astronauts outside spacecraft are less protected and more exposed to space radiation. Satellite operations. Highly energetic ions penetrate electronic components, causing bit flips in a chain of electronic signals that can result in improper commands within the spacecraft or incorrect data from an instrument. Less energetic particles contribute to a variety of spacecraft surface charging problems, especially during periods of high geomagnetic activity. Surveying. Magnetic field changes associated with geomagnetic storms directly affect operations that use the Earth's magnetic field for guidance, such as magnetic surveys, directional drilling, or the use of magnetic compasses. Ionospheric disturbances cause errors in location obtained from GPS signals. Communications. Communications at all frequencies may be affected by space weather. High-frequency, HF, radio communications are more routinely affected because this frequency band depends on reflection by the ionosphere to carry signals great distances. Dynamic and constant solar effects on Earth. Illustration of the various dynamic and constant solar effects on Earth. The two solar constants, sunlight and solar wind, takes 8 minutes and 4 days, respectively, to reach Earth. Arrival times of dynamic solar events such as flares, solar energetic particles and CMEs, are approximated and range from immediate effect to several days. Real-world examples of space weather impacts. Disruption of telegraph service on September 2, 1859. Telegraph systems across Europe and North America, which took the brunt of the impact, failed. In some cases, telegraphs provided electric shocks to operators, in other cases, their lines sparked in populated areas and, in places, started fires. Telegraph operators discovered that currents from the intense aurora borealis was flowing through their systems, causing their telegraph keys to melt and stick in position. The incident was named Carrington Event in the scientific community. The collapse of the Hydro-Quebec power network on March 13, 1989 due to geomagnetically induced currents, GICs. Caused by a transformer failure, this event led to a general blackout that lasted more than 9 hours and affected over 6 million people. The geomagnetic storm causing this event was itself the result of a CME ejected from the Sun on March 9, 1989. The Carrington event was the most intense geomagnetic storm in recorded history, peaking from 1 to September 2, 1859 during solar cycle 10. It created strong auroral displays that were reported globally and caused sparing and even fires in multiple telegraph stations. The geomagnetic storm was most likely the result of a coronal mass ejection, CME, from the Sun colliding with Earth's magnetosphere. The geomagnetic storm was associated with a very bright solar flare on September 1, 1859. It was observed and recorded independently by British astronomers Richard Carrington and Richard Hodgson, the first records of a solar flare. The Carrington event produced some of the brightest auroras ever recorded in history. People in New England were able to read the newspaper in the middle of the night without any additional light. Meanwhile, in Colorado, miners believed it was daybreak and began their morning routine. The auroras were so strong they were clearly observed throughout the Caribbean, Mexico, Hawaii, southern Japan, southern China, and as far south as Colombia near the equator in South America and as far north as Queensland, Australia near the equator in the southern hemisphere. A geomagnetic storm of this magnitude occurring today would cause widespread electrical disruptions, blackouts, and damage due to extended outages of the electrical power grid. On July 23, 2012, a Carrington-class solar superstorm, solar flare, coronal mass ejection, solar energetic particles, was observed, but its trajectory narrowly missed Earth. A global problem. The Sun and Earth are separated by 93 million miles of space, a seemingly safe distance. But since the space age began, and especially in recent years, there has been a growing realization that 93 million miles really isn't so far apart. Spacecraft and ground-based observatories have shown that Earth is located in the Sun's outer atmosphere, buffeted by solar winds and pelted by hail storms of energetic particles. Moreover, the two bodies are actually connected by invisible threads of magnetism. During reconnection events, which typically happen several times a day, you can trace invisible lines of force all the way from Earth's poles to the surface of the Sun. The Earth and Sun are interconnected.